In this video, we're going to talk about the transpose operator, and the transpose operator acts on a matrix A, say. And at this point, the transpose operator is going to be a little opaque. It's not really actually going to make sense why we want to do this. I can basically justify it a little bit, but it's going to be a little weird. So you'll have to just bear with me on this one. So the transpose operator, so if we have a matrix A, the transpose operator, we simply write a T up in the superscript. And that indicates the transpose. And what does the transpose do? Well, let's say that A was this matrix. So let's say we have our generic 2 by 2. A21, A22, A23. Well, when we take its transpose, now we're going to get a 3 by 2 matrix obtained by essentially turning the rows of this matrix into the columns of this matrix, right? Or essentially the columns of this guy become the rows now, right? So it transposes the rows with the columns. That's what the transpose does. So this gets to be A11, A12, A13, so I just read off this row, and then I have A21, A22, A23. So one reason why we could justify this, well, sometimes we have say A and B have the same number of rows and columns, right? But we want to compare the rows and columns somehow. So we'd basically like to multiply the columns of A times the columns of B, right? But if A and B are m by n, we can't matrix multiply them. Unless, say, m is equal to n, right? But we still want to compare the rows and columns, or we want to multiply all the columns times the columns of B, or all the rows, say, times these guys, right? So in order to do that, we basically had to turn the columns of this guy into rows so that we can matrix multiply against the columns of this guy, right? So we want to multiply columns of A times columns of B. In order to do that, we have to use the transpose. A transpose B. And that's going to give me a new array, right? How many dimensions? It's going to be an m by n array, n matrix of products of columns. And this quantity will actually turn out this shows up a lot, and that's very useful. But for now, it's a little opaque. Well, we need to establish some rules. So we looked at laws of matrix algebra last time. So now we need some rules for the transpose, because the transpose behaves reasonably well. But there's in particular one thing that's kind of fishy about it. So we know that, so it's pretty easy to verify this is true, is that we can essentially bring the transpose in if we have a sum. The same thing with a negation, right? A minus B transpose, well, we do that. If we have the transpose operator cancels itself out, right? That's back equal to A. So the reverse of the transpose is just take the transpose again. That's pretty clear. If we have a scalar multiple of A, and we take the transpose, well, that's just going to be equal to C times the transpose cat, right there. So these are all easy to verify. Something that's a little more complicated is how this transpose interacts with matrix multiplication. So if I have A matrix multiply B transpose, it turns out that this is equal to B transpose A transpose. Right, so that may look a little weird. And in fact, we can say that that's a theorem that we should verify. So proof of this theorem that we need to verify. So suppose A is m by p, and B is p by n, so this matrix multiplication is well defined in general. Then we want to look at the ijth entry of the transpose and see what that's equal to. Well, the ijth entry, basically because the rows and the columns are swapped, this is going to be the jith entry of A times B, because we swap these entries. We basically swap indices when we're looking at the index values of the matrix. But this is defined as, in sigma notation, the sum from k is equal to 1 to p of A j k B ki. That's just definition. But also by definition, this is if I looked at the transpose instead, I can swap this and this becomes kj, and this becomes B transpose, the ikth entry. So this is kind of weird. And now I can commute these guys. So I get B transpose ik, A transpose kj. And if I sum all those up, well, this looks exactly like B transpose A transpose ij. Right, that's exactly what that sum is. And so I've verified that any entry here, any entry of this guy, is the same as the entry of this guy. Right, so the ijth entry of AB transpose is equal to ijth entry of B transpose A transpose, and so this fact is true. Right, so when I take the transpose, I have to take the transpose of everybody, but I have to also flip the order of the multiplication. So just keep that in mind. It's a really useful fact. And we're done.